Hello and welcome to everyone joining in. A special mention to those present at the GeoTraces Summer School in Cape Town, which is currently going on. My name is Ryan Cloete. I'm from Stellenbosch University, and thanks to the committee for this opportunity, I want to spend the next 10 or so minutes sharing with you some of the work we've been doing in the Southern Ocean, specifically with regards to trace element cycling in the surface ocean. But really, I also want to highlight how the inclusion of the IDP data has really helped us to upscale these observations, and in so doing has empowered us as ocean scientists. I want to start off with a schematic of seasonal ion cycling in the Southern Ocean from Tagliabue et al. Many of us are familiar with this, but it really highlights the key physical, biological, and chemical processes that are at play when interpreting seasonal signals. So over here, starting with winter, we have this high iron stock. It's driven by deep winter mixed layers, which are sustained by strong seasonal storms and turbulence. But we see that as we progress through to spring and eventually summer, we have losses from detrainment and also increased biological uptake and abiotic scavenging processes. So really our idea here is to see how this applies to the nutrient elements. These are elements which are probably less particle reactive than iron. So the idea is to see what are the dominant processes in the seasonal cycling of these nutrient elements. Over here, I'm showing some results from some crossover stations that we did in 2015 as part of the Sussex cruise. The top panels are copper, then cadmium, nickel, and zinc. And I'm showing these crossover stations from the subantarctic zone, polar frontal zone in the middle, and finally the Antarctic zone. And really what we see from these plots is that as we move into the higher latitudes, we see the seasonal signal in the surface really becomes more pronounced and more evident, whereas below in the subsurface, the seasonal signal is negligible, as we would expect, where water mass mixing is dominating the annual cycle. Moving on to these right panels, these are Hofmöller plots. The top panel is weekly chlorophyll climatology, and the bottom is particulate organic carbon. And the top, I've shown by this black line where in the year the maximum mixed layer depth is reached. And we can see that in the Antarctic zone, in winter, we've sampled really close to this maximum level of mixing, while in the summer, we sampled in a period of quite high productivity. So the idea here is this seasonal signal caused by entrainment, or what is the relative importance of entrainment versus biological uptake? This is really where the ideas, we can upscale them with the IDP. This plot is showing all of the Southern Ocean stations that have dissolved and particulate nickel data. They're colored according to their season, and the shapes represent the different zones. And in these panels, I've split the data up into the different Southern Ocean sectors, and also shown the data for dissolved and particulate nickel. So these kinds of views highlight a lot of things. First, they highlight the amount of data that we have at our disposal through the IDP. This is all easily accessible. It's open access. There's a range of different viewing, exploration, and downloading options, which make it very user-friendly. But they also help us to identify gaps in the database and also regions where we could really focus in on our research questions based on the data availability. So we are really excited about this IDP release because the group here at Stellenbosch, we have 2 winter cruises and a spring cruise that's being included in this product. And really that's been our goal over the past years, is to really focus on the winter, or the transition between seasons, and utilizing the Cape Town's geographic advantage to the Southern Ocean. So looking at this data with latitude now, I'm showing the 4 different metals. Again, the colors are the seasons and the shapes are the frontal zones. And the common trend through all of these elements is we see that these mixed layer concentrations are increasing as we move south, as we would expect in the Southern Ocean, with the upwelling of this nutrient-rich circumpolar deep waters to the surface. But what I really want to highlight here is that because the data in the IDP are of such high quality, they're comparable. This allows for seasonal observations, which are at the sub-nanomolar and even below. And this is thanks to years of sampling and analytical developments, but also rigorous review, which allows us to have this confidence in the trends that we are seeing. So if we move to some calculations and visualizing the data in a bit more of a quantitative manner, here I've compared winter and summer seasons from the Antarctic zone, where we see the strongest seasonal signal. I've listed the concentrations, the means for summer and winter, but I've also compared the ratios of the elements to density. And generally, all of these comparisons here are statistically significant. And so the difference in the element to density ratios shows that it's more than just a water mass signal that is controlling these seasonal variations. So what we've tried to do here is estimate the trace element uptake between the seasons and then compare it to the measured difference to see what is the importance of the biological signal in determining this seasonal variation. To calculate the estimated uptake, we have taken the seasonal difference in phosphate and multiplied it by the cellular metal to phosphorus ratio in the cell. Now, typically, these cellular quotas are very difficult to come by and very difficult to match to the phytoplankton community present during our sampling. So again, we can draw on the IDP data, and here I've plotted particulate trace element to phosphorus ratios. I've backed out the lithogenic component, so I've plotted this as excess. That was done using particulate aluminium and upper crustal compositions. And we see here we have different colored lines. The black line is the mean for all the data, and the different colors are related to the different zones. And we'll see that this is really important throughout the metals, because depending on which zone you have this different elemental stoichiometry, which is what we would expect with the changing communities across the Southern Ocean fronts. So I've used the Antarctic zone derived ratios, and what we find is that the biological signal can explain between 70 to 110% with an error of the seasonal signal. And so this is really useful, and we're really looking to build upon these hypotheses as the new IDP comes out. And lastly, just a thank you to GeoTraces, firstly to the leadership, to the data assembly, and everyone involved, the unsung heroes of the program. The GeoTraces community, I thought I'd add this photo in from the first GeoTraces summer school in Brest in 2017. I was present as a young master's student, and many of you tuning in were there and will recognize yourself and have a nice throwback. But really, it's been such a great community to be a part of, and thank you to all the mentors, the colleagues, and the friends over the years. And then to finally the funding bodies, without which none of this would be possible. So thank you for your attention, and really looking forward to getting stuck into this new data set.